Okay. Okay. Hi, everyone. Thank you for attending this talk. Like I said, today I'll be talking about how we can use causal inference and data management to address some of the most important challenges in responsible data science, including algorithmic fairness and algorithmic transparency. Let me start by quickly defining what do I mean by responsible data science and motivate my research and the topic of this talk. So I think we're all excited about data, and I think we are all agree that the ultimate goal in data science is to extract value out of data and turn it into actionable insight that can be eventually used for making decisions that improve people's life, from business to healthcare and education, all the way to justice system. However, as you may know, there are several examples of data-driven analytics being used for making consequential and high-stake decisions in the context of risk assessment, employment assessment, and healthcare that are non-transparent, faulty, and discriminative. Therefore, there is an interesting concern about responsible use of data. In data science, now we are facing new challenges and important questions such as how we can ensure that the conclusion that we make out of the data science pipeline, they are fair, valid, accurate, and reliable. How can we build transparent systems so that our conclusion becomes indisputable and the customers and end users would trust our systems? Now, these challenges are widely referred to as responsible data science, and the goal of my research is to find principled way to address some of these challenges. Like I said, my background is in data management. I'm basically a part of data management community, but I'm very much interested in causal inference. This is basically the pipeline that I look into in my research. As I'm going to discuss later today, fundamentally, we have raw data. We are going to pre-process data, and we are going to make it ready for analysis. In order to analyze our data, we are either running some sort of analytical queries or fancy machine learning or data mining algorithm. And then we use the results for decision making. There are actually lots of things that can go wrong during this pipeline that could potentially lead to invalid, faulty, and discriminative decisions. Sometimes, as we are going to discuss in the first part of the talk, the problem is with the existing raw data. And my work in the context of algorithmic fairness addressed this issue basically by developing or using database techniques to developing a sort of data cleaning algorithms for the purpose of machine learning. So the goal of these data cleaning algorithms are somehow to remove discrimination signal from training data in order to be able to build fair machine learning algorithms. Sometimes there's nothing wrong with data. There's absolutely nothing wrong with data, but it might sound counterintuitive, but I argue that even if the input data is totally bias-free, each and every step during the data preparation, for instance, during data cleaning, data integration, data filtering, any sort of transformation, feature engineering, they can actually introduce bias out of the blue or exacerbate the existing bias signal in data. My ongoing work in the context of the work that turned responsible data management aims to address these sort of biases that some people call technical biases. Sometimes there's absolutely nothing wrong with data, but as I'm going to show today in the second part of the talk, users ask queries that are inherently biased for decision making. In the context of decision-making system, I develop systems that assist business decision makers to avoid false queries and hence false conclusions. And then I believe generating explanations are crucial for trustworthy data analysis and for understanding data. I have several ongoing projects that look into generating explanations for black box machine learning algorithm. In the last part of the talk, I'm going to discuss my most recent work in this context. And then in addition to data management, my research is grounded in causal inference because hopefully, as I'm going to convince you today, causal inference can form as foundation for algorithmic fairness, responsible data management, avoiding false conclusions, and for generating explanation for black box machine learning algorithm. But I also contribute to the causal inference literature by developing a scalable algorithms for causal inference and by providing and developing the foundation required for causal inference from complex relational data that I'm going to touch a little bit today. During the past few years, I've built several systems that address challenges related to responsible data science. Today, the main focus of the talk is going to be on Capuchin, which is a system for building fair machine learning algorithm. Then I'm going to talk about HeapDB, which is a system that assists business decision makers to avoid false conclusions. And finally, I'm going to discuss a little bit about my most recent work in the context of causal inference from relational data and explainable AI. Okay, let's get it started. I'm going to start with a very gentle background on algorithmic fairness and causal inference, which is required throughout this talk. Okay, so let's start with the question that why should we care about fairness in data science? Isn't it that algorithms are objective creatures? How can they be racist or sexist? Well, that's true, but you should pay attention to the fact that the input data to the data science pipeline is data being collected from societies that are polluted by years of institutionalized racism and discrimination. Now, in order to analyze this data, whether you use a simple analytical OLAP or SQL query, or a fancy data mining or machine learning algorithm, these algorithms are going to reflect what is in data. They are going to pick up the existing discrimination signals and become discriminative. One notable recent example is Amazon recruitment tool that turned out to be basically a male detector and highly discriminative because of the historical bias in their training data. And they had to actually shut down the project because they had no idea how to fix it. Let's discuss this. Let's see how we can address the issue of fairness in data analysis. In order to be able to reason about fairness, to detect it and to address it, to remove it from the results that we get out of the data science pipeline, we need a computational definition. Today, I will focus on fairness. Of course, fairness can be defined in various contexts. We are only going to focus on fairness in the context of decision procedures that can be seen simply as mappings between an input space to an output space. Today, we are going to assume, for simplicity, that output is just a binary output, 1 for positive outcomes, 0 for negative outcomes. And then we further assume there is a sensitive attribute, which again, for simplicity, we assume it's a binary sensitive attributes. S equal to 1 stands for protected groups, and 0 stands for privileged group. These sensitive attributes, we are going to assume it's associated with the input feature space. There's a plethora of definitions for defining fairness for this simple context. You may have heard about lots of fairness definitions in machine learning. These definitions basically define fairness. The intuition behind these definitions is as follows. They basically define fairness in terms of sort of a strong statistical association or correlation between sensitive attributes and outcome of machine learning algorithms or their precision. For instance, the most popular and famous notion of fairness is called demographic or statistical parity, which simply requires the positive outcome of algorithm to have the same proportion for privileged and protected groups. In other words, it requires no statistical correlation between the sensitive attribute and outcome of machine learning algorithm. It requires them to be statistically independent. There are slightly more complex definitions of fairness. For instance, equalized odds. It requires the same ratio of false positive and false negative, and predictive parity requires each class of output of algorithm to have the same proportion for privileged and protected attributes. They're slightly more complicated, but they follow the same principle, meaning they are based on statistical associations. The first one is based on statistical demographic parity, concerned about the statistical association between sensitive attribute and outcome. Equalized odds, concerned about the statistical association between sensitive attribute and false positive or false negative reads. Okay, so what's important here is these definitions turn out to be inconsistent and highly counterintuitive in general. Inconsistency means it's impossible to satisfy them all of them at the same time. And counterintuitive means there are lots of examples which shows that these definitions cannot capture the social idea behind fairness. Today, I'm going to share with you one example which essentially focuses on demographic parity, but the same observation applies to all of these fairness definitions that are based on the statistical associations. Okay, let's go through a very simple example. It's a very famous, but probably encountered it in other sort of contexts. In 1973, UC Berkeley were accused for discrimination. in student admission based on the fact that in that year, as you observe in this graph, men were more likely to get admitted to Berkeley than women. And the margin between them, the margin of ratio between them was so huge. So it wasn't just, it was statistically significant. In other words, in that year, Berkeley violated a statistical parity, which means there was a huge correlation between gender and admission to Berkeley. So this graph clearly suggests that there is a huge disparity against female. There was a huge disparity against female in that year. But it turns out that if we compute these admission results, now by each department, suppose we only have 6 departments, these are actually real data. Now, if you check out each particular department, it is actually female that have a better ratio, higher ratio in a particular department. Now you're in a situation in which your first graph suggests a strong disparity against female, and all of a sudden the second graph suggests disparity against male. So this phenomenon is known as Simpson's paradox, and what it shows us, what it tells us here is it is impossible to capture the intuition behind fairness, which is a social idea, using a statistical association. We need a more richer, actually, language to be able to reason about fairness. In this case, what we get from data is a strong association or correlation between admission results and gender. However, if we want to understand whether this correlation is an indication of discrimination or not, we need to understand why they are correlated. And here's where causality comes into the picture. Causality can be seen as a tool that can actually answer these sort of questions, these sort of questions, can generate explanation that tells us why admission results and gender are highly correlated. In order to answer these questions using causal inference, we start by encoding our background knowledge about the domain from which this data is collected using a very simple language, using a language of graphs or directed acyclic graphs. It's a very simple language in which nodes in a graph represent variables in our domain, and there is an edge between them. There's a directed edge between them if we believe there's a causal relationship between variables. Let's go to an example. In this case, we have 3 attributes or 3 features: applicant's gender, their choice of department, and the admission results. And then we know that, I think this is a common knowledge that all of us share. So we know that, of course, choice of department depends on several factors. A student's choice of department depends on several factors, one of which could be applicant's gender. It's just an assumption that we are encoding here. We are not sure yet, but this is basically a very reasonable assumption to make. Similarly, admission decisions are made by each department. Each department have their own admission committee, so we have an edge here. Admission results are influenced by each department. And it's based on several factors, right? For instance, the student's qualifications. But in addition to those factors, it could be also a function of gender, right? Which means admission committee members, they might be influenced by applicants' gender. In which case we say the admission committee is discriminatory because they're influenced by gender. But here's the thing. The data could be generated in a domain which is exactly identical with this, but in the second one, there is no edge from gender to admission result, which means admissions committee are totally agnostic to applicant's gender, right? In which case you may say this is a non-discriminatory admission committee. But now here's the punchline. In both of these scenarios, in both of these basically colleges, we expect to see a huge correlation between admission results and gender. In other words, both of them violate demographic parity. But we just basically argued one of them seems to be discriminatory, but one of them seems to be not discriminatory. And that's why I argue a statistical association is insufficient for capturing fairness, because, for instance, violation of demographic parity here does not enable us to distinguish between these 2 cases, right? We need a machinery that enables us to be able to distinguish between these 2 cases, to understand whether gender directly influences admission results or not. And here's where causality actually helps. We can use the secret sauce of causality, which is reasoning about interventions. Using interventions, we would be essentially able to answer questions such as what would be some outcome of interest if we manipulate, change some other variable. Let me go through an example. Using these interventions, we can now answer very complicated and complex counterfactual questions such as what would be the probability of admission if all applicants are female, which is basically captured and denoted by this probabilistic formula, which has the do operator or do notation, which is a formal way to capture interventions in causal inference, in parallel causality. Let's discuss what exactly we mean by these interventions to make it clear. One simple way to conceptualize these interventions is to assume, just for the sake of assumption, that we have this additional hypothetical attribute in our data that record admission results in a counterfactual or hypothetical world in which all applicants were female. For instance, this value right here, it basically records, the first entry records the admission results for the first student in a hypothetical world, just an imaginary world in which this student were female, but this student is actually a male. Similarly, for the other students, this attribute records what would be the value of their admission, what would be the result of their admission had they were female. A statistician refers to this attribute as potential outcome. Similarly, we can answer the same question for males. What would be the probability of admission if all applicants were female? Now, in a second word, in pink, we record admission results for all the students in a hypothetical world in which all of them are male. Causal influence of gender on admission results can be actually computed by comparing the outcome in these two words. Simply because in these two words, students are exactly the same. These two words agree on everything, except for the fact that in one word, all the students are female, and in one word, in the second word, all students are male. Therefore, if we observe any sort of discrepancy between the admission results in these two words, we can attribute it causally to applicant's gender. And this is how actually causal inference can be used to reason about the causal inference of protected attributes, sensitive attributes on outcome of an algorithm, and to capture fairness. Okay, so this is so simple, right? If we had these two potential outcomes, we would be able to compare them by taking the averages, for instance, right? But what's the big deal about causal inference in general? Causal inference is complex and complicated because, look, for each of these students, we only observe one of these potential outcomes. For instance, for the first student, we had no idea what would be the admission results for that student had that student were female. But the student is a male, right? There's no oracle that tells us what would be the admission results in that imaginary world. Therefore, causal inference, in a sense, is a sort of missing data problem, right? The goal is to see under what assumptions and under what assumptions or situation we would be able to impute these missing variables. And if we would be able to impute them, we would be able to do causal reasoning. A gold standard for inferring these missing values is conducting randomized experiments or controlled experiments or A/B testing. Since you have background in industry, people in industry call them A/B testing, in which the subject of analysis are basically randomly assigned to treatment or placebo. In the context of a running example is being female or male, and then the result of these randomized experiments under some assumptions enables us to do causal inference. But in general, doing causal inference using randomized experiments is, in some cases, very expensive. It's even unethical. Suppose you want to measure the causal inference of smoking on lung cancer, or even impossible in this case. How do you want to distribute gender randomly to students, right? It's not even imaginable or conceivable to do randomized experiments. In the absence of randomized experiments, what we can do is using causal inference from observational data. Fortunately, under some assumptions, we would be able to estimate these missing values from observational data that is collected passively without any randomized experiments, like I said, under some assumptions. And the principal way to formalize these assumptions and to evaluate them is using Pearl's causal inference engine. Let me quickly explain what parallel causal inference engine is all about. Input to the parallel causal inference engine is observational data and background knowledge about the data generative process. Whatever you know about your domain, how the data is generated, the properties of those domains, the variables and your assumptions about the causal relationships between those variables in your domain. Given this background knowledge and data, upon the arrival of a query, which is a causal query, it asks about the effect of interventions. The engine tells us under the assumptions that we have infinite data. Suppose there's no problem. We have all the data in the world. Whether under this assumption, it is possible to answer to this query. In some cases, it is impossible to answer causal queries, even if you have unlimited data. Even it's impossible, some causal queries are impossible to answer, even if you can perform randomized experiments. But if the answer to this part, to this module is yes, parallel causality gives you a recipe for estimation of your causal query. The recipe is basically a complicated probabilistic formula, which is an integration over the product of a bunch of conditional probability distribution that now you can go ahead and use your favorite, the statistical estimation or machine learning algorithm to estimate it from observational data. Okay, so with this background in place, let's get to the first project, which I'm going to discuss, Cappuccino, a system for building fair machine learning algorithm. Okay, so in this project, we looked into the following problem. How can we ensure that machine learning algorithms are fair? We particularly focused on a prediction algorithm, a classification or regression algorithm, and we focus on one type of biases, bias due to pre-existing or historical bias. The thing is, data can be biased for several reasons. Sometimes the data generative process, the process that generates training labels are biased. Sometimes bias occurs because of other factors, for instance, during data collection, for instance, selection bias or measurement bias. We don't talk about them today. We're only going to focus on pre-existing or historical human bias. And then the main idea we sort of promoted in that work was we need to deal with these sort of historical bias, which is encoded in training data at upstream by sort of repairing or cleaning data. Think about it as a data cleaning problem. So that any sort of use cases of these training data downstream in the machine learning pipeline or data science pipeline can achieve some sort of fairness. In particular, we propose a novel notion of bias, which improves the existing definition of bias. And like I said, we reduce the problem of building fair classification algorithm to a sort of database repair problem. If the database, if this repair term is unfamiliar to you, think about it as a cleaning problem. Data cleaning problem. We want to clean data to remove discrimination signal from it so that if you train a machine learning algorithm on top of these clean data, now all of a sudden it becomes fair and not discriminative. Okay, so let's just start by discussing the definition of fairness that we propose. It's a causal definition for sure. We already argued we need causal inference to be able to capture fairness. Before getting into the definition, I should mention that I'm not a lawyer. I have the caveat that I'm not a lawyer, and we're not going to talk about legal or philosophical aspects of fairness today. Okay, so let's expand the Berkeley example a little bit. Suppose we are dealing with the college in which admission results are based on applicants' qualification, choice of department, and also their hobbies, right? The first basically way that we can use causal inference, it's the most immediate way that we can use causal inference to define fairness, is to say we don't want any causal influence. We don't want the sensitive attribute, in this case, G, gender, has any sort of causal inference on outcome of interest. Which is very simple and intuitive. In terms of graphs, this means we don't want any directed causal path, from gender to admission results. Very intuitive and simple. In terms of interventions, this basically reads as, we don't want performing hypothetical interventions or manipulation on a student's gender. We don't want that to have any sort of influence on application results. This basically means pick one student, hypothetically change the gender of that student, see whether that affects or changes its application results. If so, we say there's a causal relationship going on. If not, we say there is no causal relationship going on. This can be seen as a sort of causal counterpart of demographic or statistical parity, in which instead of conditioning, we are doing intervention. Okay, this notion seems to be very appealing at the first glance, but I would say, like, no matter if we like it or not, sensitive attributes such as age, gender, and even race, they influence many factors. For instance, in this particular example, gender may influence applicants' choice of department, right? Because students have the free will to choose different departments. And then gender also influences students' hobbies, right? And we sort of don't have any control on these sort of association or statistical or causal influences. Like I said, gender influences applicants' choice of department, and since application decisions are made by each department, so in a sense, the causal path in green is unavoidable, which means gender influences admission results anyways through their choice of department, right? And this causal path seems to be totally legit and not discriminatory. Whereas you may argue that influence of gender on admission results through their hobbies would be discriminatory. So we need a rich language to be able to distinguish between different sort of influences that sensitive attribute may have on an outcome of algorithm through these proxy variables. So in order to capture these nuances over the notion of fairness, our system enables the users to partition variables into two sets, which we call admissible and inadmissible variables. Admissible variables are intuitively those variables such that, for whatever reason, we believe the influence of sensitive attributes on outcome of algorithm through these variables are not discriminatory. And then we tag or label the rest of the variables as inadmissible. Let's see an example. In this case, one might argue that influence of gender on admission results through applicants' choice of department and through their qualification is totally fine, right? However, the direct influence or influence through hobby is totally discriminatory. So we label hobby and gender as inadmissible variables. There is no magic that tells us which variable is admissible and which variable is not admissible. We accept these as input, right? These partitioning should reflect the underlying cultural, societal, legal, and ethical consideration and could be varied across different sort of societies and countries, whatever. We just accept it as input. With this input in place, now we are in position to get to our main definition of fairness, which is called interventional or justifiable fairness, which it says something very simple. It requires basically the sensitive attributes to influence the outcome of algorithm only through admissible variables. In terms of intervention, this basically means for fixed value of these admissible variables, in this case, once we fix applicants' qualifications and choice of department, perturbing or changing or intervening gender should not influence outcome of algorithm, which means it is impossible. Sensitive attribute only influences outcome of algorithm through admissible variables. There is no pathway which is not intercepted with admissible variables. In this case, let's discuss this case. In this case, obviously there are two passes, those passes in red, that are not intercepted by admissible variables. We have two passes, two influences. One of them is direct influence. Gender influences admission result directly, which is totally discriminatory and should be forbidden. And we have another influence, which is through applicants' hobby, right? But the causal path in green is totally legit and fine because it is through admissible variables, right? So this college we declare this college as discriminative, right? Because it violates our notion of justifiable fairness. Okay, so with this definition of fairness in place, now we get to the main problem. Here's the main problem that we want to solve. Suppose we have collected historical data from this college, and we want to sort of train a machine learning algorithm that approximate admission committee decisions. We want to replace admission committee by a machine learning model. We just discussed the admission committee itself is discriminatory. So the data reflect the underlying discrimination, the discrimination made by the admission committee. And if we now train a machine learning algorithm, the machine learning algorithm, if it's accurate, is going to copy the admission committee, and it's going to basically replicate the discrimination, and it becomes discriminatory. The main question now that we want to answer is the following: whether it is possible to use this historical bias, which is historical data, which is totally biased. Can we use that historical data to train a machine learning algorithm which is unbiased? That's the question that we want to now discuss, and we answer positively to this question. And here's the intuition behind the answer. Of course, we cannot change the word. We cannot change the causal model, right? We are computer scientists, we're data scientists. We don't have the ability of changing the word. Maybe we can change the word through our algorithms, but we cannot change the causal model, right? But what we can change, we have total basically control and governance over data. Can we start to change the data in a way such that the changed data, the manipulated data, reflect the work, the admission committee as we wish we had? Can we change data and fool the machine learning algorithm as if the data, the manipulated data, is collected from a fair committee, fair admission committee, or fair college? Let's discuss what do we mean by wish. What is the admission committee that we wish we had? We wish we were dealing with an admission committee. Let's pay attention to that graph, please. We wish we were dealing with an admission committee in which the admission decisions were not based on applicants' gender, and were not based on applicants' hobby, right? If we were dealing with this committee, everything was fine. The data would have been totally unbiased. We had no problem, right? Now the question becomes, given this knowledge, how can we leverage from this graph to be able to do this manipulation, change the training data, so that we can fool the machine learning algorithm as if the data were collected from this graph. So if you're not familiar with graphical models in general and causal inference in particular, the missing edges in graphical models or in causal models encodes a very important and fundamental assumption. It encodes two variables that are not connected through any edge. It basically means they are conditionally independent on another set of variables. And this notion of conditional independence is fundamental in the statistical machine learning. In this case, if you're not familiar with conditional independence, I'm going to explain it in a second, don't worry. In this case, the missing edge between, for instance, edge hobby and admission results encodes the following very intuitive conditional independence. It encodes that once we know applicant's qualification and applicant's choice of department, given applicant's choice of department and qualification, the admission results, right, is going to be independent of applicant's hobby and applicant's gender. This is what I mean. What do I mean by conditional independence? Think about information. Think about it through information theory. It means once we have knowledge about applicant's qualification and their choice of department, then all other variables become irrelevant. We don't need to know anything about that. Knowing hobby and gender doesn't give us any sort of information about admission results. And it is somehow clear that why this is an appealing and interesting property from the perspective of algorithmic fairness. So this graph encodes the assumption of conditional independence, and this is basically the assumption. This is basically the knowledge that we can use to generate the data D prime, the manipulated data that we are looking for. We basically do this manipulation using data management, because in data management, I don't want to get to the technical discussion of the data management part of this project, but manipulating integrity constraints in data management is actually a very important problem to keep the integrity of data. There are various sorts of dependencies in databases, such as functional dependencies, multi-value dependencies, conditional functional dependencies that people use in order to make sure that the integrity of their data is a very important topic in data quality. And in a sense, this conditional independence can be seen as a constraint, right? We want the data to satisfy this constraint. And this is the insight that we use to essentially turn our fairness problem into a data cleaning or database repair problem. The bottom line is we want to somehow manipulate data in terms of removing some data points or inserting some sort of synthetic data points such that the new data, B prime, satisfy our conditional independence, which can be seen as this multi-value dependency. It doesn't matter what multi-value dependency is. It's another sort of representation for conditional independence. So let me backtrack. We discussed fairness can be captured in terms of a sort of conditional independence, right? Which can be seen as a constraint. And then we can manipulate data such that the manipulated or clean data, such that the clean data now satisfy this constraint. And this is basically the problem that we addressed in that paper. We showed that doing this sort of data cleaning in a minimal way. Why we care about minimality? Because we want to actually preserve the utility of data. At the end of the day, we want to have a model which is as accurate as possible while it satisfies this fairness constraint, right? So it has to be, we need to manipulate data in a very minimal way. We showed that this problem is NP hard. If you're not familiar with this complexity classes, basically means it's very unlikely that we can find a tractable algorithm for it. And in order to deal with this, we proposed reduction to max sets because we wanted to use max of solvers. There are lots of solvers, efficient solvers out there that can be used. And we also used low rank matrix factorization to address this repair problem. And we showed that, more importantly, any classifier that trained using repair data after we do this sort of cleaning, it's going to be causally fair even on unseen test data. Okay, so let me share with you a very quick example. So in order to see whether this idea would work in practice, we picked up adult census data, which contains information about individuals, demographic information such as their occupation, education, marital status. And the task is to predict whether individuals receive high income or low income. For the sake of, now, what we want to make sure that we are training a classifier which is fair. And what do we mean by fairness here? For the sake of demonstration, we assume the influence of sensitive attribute, in this case, gender, on outcome of algorithm. We assume all variables are admissible except for marital status, which means we forbid the direct influence of gender on outcome, as well as its indirect influence through marital status, which basically means it's okay if gender influences outcome through other variables, for instance, through their education, right? So in a sense, we used our system to remove these two discriminatory or red passes here by changing data. Let's see how this idea would work in practice. This graph shows the utility versus bias of the model that we trained on raw data and on repair data. Let me tell you what the graph shows here. The utility is measured by accuracy, to what extent our model is accurate, and bias is measured by causal bias. It doesn't matter exactly what it is. What matters is 0 shows no discrimination, while 1 shows maximum value of discrimination, right? So in a sense, the ideal scenario should be somewhere here, right? We want to have to end up with a model which is very accurate, but not biased at all. As you observed, the maximum accuracy is achieved by the original data, training data, raw training data, but it is, as you see, it's very biased, right? It's biased, but accurate. But after we repaired training data, by removing all those discrimination signals that we just discussed, we observe that at the cost of only 2% of classifier, we can reduce the discrimination basically almost entirely. 98% of the bias is reduced, right? In this case, for instance, in the case of this repair method, which uses low-rank matrix factorization. It is almost perfectly biased. This residual bias is basically a product of finite data, just random noise. But as you see, we only paid 2% of the accuracy of the classifier. So yeah, it worked. Let me conclude the first part of the talk. What we have discussed on algorithmic fairness. We discussed associational notion of fairness. There are lots of them in the machine learning literature. They are inconsistent. They cannot capture the social idea behind fairness. Discrimination and fairness is a fundamentally causal concept. We need causal inference and interventions and counterfactual in order to be able to capture fairness. And then we also kind of discussed that we can enforce these fairness, we can see these fairness concerns as sort of constraints, conditional independence constraints, and then we can clean and repair data to satisfy these constraints in order to be able to build fair machine learning algorithm. Any questions so far?
Professor Salimi, this is Ted. So if you ran this algorithm and
Mhm.
the matrix factorization algorithm told you you didn't need to change the data hardly at all, would that then be a sign that your original data set did not have um, you know, prior biases baked into it?
Absolutely. You can essentially start by detecting bias, and detection of bias has to do with it amounts to performing a bunch of conditional independence tests, right? You can first check whether the independence holds or not, and if it holds, there is no need to run the cleaning algorithms. But you are right. Even if you skip that step, if you directly run the matrix factorization algorithm, it doesn't change anything. It's a sort of rank 1 matrix factorization. If your matrix is already rank 1, the factorization is going to be identical to the input, right?
Okay, thank you.
Sure. If there's no other question, let me get into the second part, which is going to be a short description of 3 projects. First one is our work in the context of decision-making systems. So I think you're all familiar with business intelligence tools such as Tableau and Power BI. Many of you, I think, use these sort of methods, or sorry, tools on a daily basis in order to get insight from your data. These tools, they collect and process large amounts of different modality of data, structure, unstructured data from different sources, and help business decision maker for improved decision making, primarily through analytical SQL queries, reports, fancy dashboards, and data visualizations. When it comes to decision making, this is basically what they promise. We put data into action. I actually took that statement from Tableau website, and very quickly, I'm going to share with you an example, which hopefully convince you that this is pretty much what they deliver. They're not able to answer the most basic questions that you may have in business. And let's see why. Okay, suppose we're going to discuss everything in terms of a example. So suppose we're dealing with a company. You have a company which has many business travels from 4 airports, just 4 airports in the United States, and you want to sign up for business travel programs offered by either American or United Airlines, right? So the question here is basically, the decision here depends on the answer to the question that which airline has a better on-time performance. And in order to answer this question, you ask your data analysts to use publicly available flight data and use Tableau to answer this question, this SQL query. If you're not familiar with SQL, what this query basically says is it just measures the average of delay, the average of delayed flights in the context of 4 particular airports that we're interested in, grouped by the carriers. What's the average delay of United Airlines and American Airlines? Because just simply want to compare the average delay of these 2 airports. And thanks to amazing performance of Tableau, this is what we get in a blink of an eye. And as you observe in this graph, American Airlines has a much lower flight delay, right? So based on this, you may come across to the conclusion that American Airlines performs actually much better, at least in the context of those 4 airports. But now the data analyst, just for the sake of, just out of curiosity, it further compares the delay of these 2 carriers in the context of 4 airports that we care about, right? And all of a sudden, now in each particular airport, it is actually United which performs better. We are in a very similar situation that we've been to in the case of algorithmic fairness. First graph suggests American Airlines is better, and second one suggests United Airlines is better. Which one's better at the end of the day? Another instance of Simpson's paradox, which now tells something different. It essentially says all these SQL queries, all these fancy dashboard visualizations, descriptive statistics, they are not suitable for decision making. They can be perplexing and lead to false conclusions. This motivated us to develop HeapDB, which is a system that essentially discovers whether these sort of OLAP queries, or SQL queries if you're not familiar with OLAP, whether they're susceptible for these sort of biases. And if so, it generates explanations to further convince the user that these queries might be biased, and what we get out of their results could be totally misleading. And finally, it kind of repair now data. In the first part of the talk, we repaired data, and here we repaired the query. It sort of changed the query, right? It's sort of rewrite the query, change the query into another query which is bias-free and support decision making. I don't have time to go into the details. Let's brush all the details here. Let me quickly demonstrate how HipDB performs in a running example. You can think about HipDB as sort of middleware between the user and SQL query and a database system. Upon the arrival of this SQL query, it inspects the query. It automatically checks whether this query could be potentially biased. And if so, it red flags the user and says, okay, this query can be potentially biased. And if you and generate a bunch of different types of explanations to somehow convince the user that this query is biased. I don't want to get into the details of these explanations, but explanations generated for this particular example by our system essentially mention the following things. They essentially say United Airlines frequently flies from airport such as Rochester Airport that has several delays due to weather-related issues. And American frequently flies from airports such as McAllen Miller that has very few delays. So what this means, it means that this difference that we see between American Airlines and United Airlines, it's not because of their performance. It's because they disproportionately serve Rochester Airport and McAllen Miller. So it has nothing to do with their performance. Potentially has nothing to do with their performance. It just has to do with the fact that they serve Rochester and McAllen Miller disproportionately. It's because of weather at the end of the day. It's not because of their performance. And this is what exactly this is why exactly I call these queries are biased in general. In order to address this, our system performs some sort of underlying analysis to extract and discover all factors or features that can contribute to this bias and rewrite the query to account for these biases. In this case, the factor that is the most important one is the fact that they serve disproportionately, they operate disproportionately to different airports. We account for these factors and rewrite the query so that the answer to this rewritten query is unbiased under certain assumption. In this case, the answer to the rewritten query shows basically it is actually the United Airlines, which performs slightly better, which is totally different from the insight that we got from the original query. And now there is no Simpson's paradox because this is totally consistent with what we observed in the second graph. Okay, so with this, let me now jump into the third project, which is called a system for causal inference from complex relational data. The existing theory of causal inference, we have basically two clans in causal inference literature, one led by Julia Pearl, who's a computer scientist, and one by Donald Rubin, who's a hardcore statistician. These theories, they rely on two restrictive assumptions. So the first assumption is the domain of analysis basically consists of a bunch of homogeneous units. We have a bunch of students, bunch of patients. We cannot have both student patients at the same time, or both students, instructors, and faculty members at the same time. And the second one, which is more slightly more trickier, is they assume there is no causal interaction between the units of analysis, which essentially means treating, like in the context of healthcare, which means treating one patient cannot influence the outcome of other patients. Vaccinating one patient should not influence the recovery rate of the recovery rate of other patients, which is an unrealistic assumption when we have complex relational structures in which units interact with each other and causally influence each other. So yeah, the first assumption, like I said, is homogeneous entities. The second assumption, no interference between the units. But like I said, in real world, we are dealing with relational domains. The relational domains that consist of heterogeneous entities that exhibit complex underlying causal model with network dependence, interference, contingent, and homophily, if you're familiar with social networks. Let me get into a very simple example to clarify what I mean here. Suppose you're interested, the question has to do with fairness. Suppose you're interested to see whether authors' institutional prestige, define prestige by whether they are affiliated with the top ranking university or not. Whether does that has anything to do, whether does that influence paper acceptance in different conferences, whether reviewers influenced by prestige of the authors who submitted the paper. This is clearly a relational domain, consists of entities such as person, author, institution, submissions, and there is a complex relational connection between, for instance, authors, because I don't know, there's some of them, they're colleagues, we have advisor relationship, we have this complex collaboration network. All those assumptions would fail in this case. And believe it or not, we don't have a comprehensive theory to support these kind of simple questions. This motivated us to introduce CARP, a system for inferring causality from relational data. At the core of our system is a logic-based language based on data log, using which user can essentially declaratively express what they already know about the relational domain and what they want to know. And it is the underlying inference mechanism that computes the answer. So it's a declarative language, and it makes analysis, causal inference, accessible to users with no background knowledge in causal inference and statistics, which is the beauty of, in general, any sort of declarative system. I'm not going to delve into the detail here, but just to give you a sense of what goes on under the hood in CARL, I included this slide. It's very dense, but what it says is essentially very simple. It shows the reasoning pipeline in CARL, the input to our system. Using the system, user can express their background knowledge by a bunch of very, very simple rules, which they're called relational causal rule. For instance, in this case, this rule right here, it basically looks so scary, but what it says is a score of a paper, review a score of a paper, is influenced by prestige of their authors, the prestige of authors who basically wrote that paper. It's just a very simple logical rule which expresses that. Given this background knowledge, our system compiled those rules, detected those rules and the underlying relational data, and compiles them into what we call relational causal graph. Using this relational causal graph, we perform sort of, we somehow denormalize or flatten these relational data to create these flat tables using techniques such as graph embeddings, aggregation, and traversing the underlying relational structure. The output of the system is basically a flat table that you can now perform any sort of existing causal inference techniques on top of it. Let's go through an example. So we use real data, real open review data, to basically answer the question that we just discussed, whether author prestige has any sort of influence on reviewer score. It's a fairness question. It's an interesting question. We applied CARL to see whether this would be the case or not. And then we compute the answer to this query in two different domains. In the domain of conferences, there are single blind, which means the reviewers know the authors, but not vice versa. And double blind, in which the reviewers do not know the author. And this is what we observed. We observed a huge correlation between prestige and reviewer score in both conferences, both single blind and double blind conferences. But here's the interesting part. Once we used causal inference, once we performed causal inference using CARL, we figured there is no significant causal inference between prestige and reviewer score in the context of double blind conferences, but it is a huge and significant influence in single blind conferences, which basically suggests double blinding actually reduces bias, which was interesting. Okay, the last thing that I want to mention about this causal inference thing is if you have a complex relational data which looks something like this. This is a ER diagram of complex relational data. If you have queries similar to what we just went through in the context of effect of prestige on output of on reviewer score, and if we're answering these sort of queries, you just join these tables, run a SQL query on top of a flat table, it's a single table, then your analysis is most likely biased. Feel free to drop me a line. I would be happy to discuss why your analysis is biased over coffee. This gets me to the last topic that I want to discuss today. How much time do I have, Ted?
So we have 19 more minutes till the scheduled time for this session.
Perfect. I have enough time to go through the last topic then. Okay, so the last thing that I want to discuss is explainable AI. It's a hot research area in machine learning, not just in machine learning, in many communities, including my community, which is data management. Like what we have discussed, algorithmic decision making is increasingly being used for making consequential decisions in the context of hiring, loan application, healthcare, justice system. And this system has been shown to be highly accurate for many of these applications. But this performance comes typically at the cost of opacity of these models. These machine learning models are algorithmic systems. Many of these models are hard to interpret or are totally non-intuitive due to their complexity or proprietary nature. However, in order to increase societal acceptance of algorithmic decision making, it is essential to build trust among different stakeholders of these systems, starting with developers of the system who wants to build better model by running these model diagnostic tools, to practitioners who use off-the-shelf machine learning algorithms for various tasks, all the way to end users that are affected by these systems, right? These decision-making systems, they're making consequential and life-altering decisions, all the way to businesses that deploy these systems. We need to generate explanations that justify algorithms decisions and can be used for debugging models and help end users to understand algorithms in terms of internal logic and to take action to change their results in future. Generating these explanations are crucial for building trust. Let's go through an example. Suppose, imagine a bank that has customers applying for loans, very typical scenario. Depending on customer's profile, the bank decides whether to grant them loan or not. And like many other organizations today, it's very likely that banks run a machine learning algorithm that predicts something relevant. In this case, it would be, for instance, credibility of customers to pay off their debts, right? They run this algorithm, and based on the scores generated by this algorithm, they make decision to either reject the loan application or approve it, right? So in this case, at least from the perspective of end user, we want to basically tell the end users what are the reasons behind those decisions. Why did the system make these decisions? And in the case such as for which the applications got rejected, we want to actually provide explanations to user in the form we somehow suggest and recommend a set of actions so that they can make those actions, they can take those actions and change the result of algorithm in future. This is called algorithmic recourse. How can a user improve their chances for a favorable outcome in future? Recourse are super important for building trust, but aside from trust, I'm sure many of you know this, generating explanation is also mandated by law. For instance, the European Union GDPR empowers individuals with the right to demand an explanation of how an AI system made a decision that affects them. You can find numerous sort of laws and bills in place across different countries and jurisdiction with the same requirement. So it is mandated by law. It's just if the argument of convincing users is not basically convincing, it is mandated by law. We need explanations. Okay, it's a very hot research area in explainable AI is a very hot research area in machine learning. There are different sorts of methods that have been proposed for generating explanations. Today, we're only concerned about sort of explanations that treat machine learning algorithms as black box, right? They're called post-hoc model agnostic explanations. They're model agnostic. They make no assumptions about the internal of a model. They only assume access to the input and output of these systems. This is what we are going to focus on. There are various methods proposed for generating these post-hoc explanations, post-hoc model agnostic explanations. The most popular ones are based on feature importance, which follows a very simple idea. Just rank this feature, quantify the influence of different inputs. For instance, in this case, The inputs are name, age, saving, months, credit history. Just rank them based on importance. Now, what do we mean by importance? There are different definitions. The most popular one is shop, which is a thing. I know that someone, your last speaker discussed shop, I think, in the last months. It's a game theoretic notion. I don't want to get into the detail, but that satisfies many sort of desirable axioms. So that's why it is a very popular sort of methods for performing this sort of feature attribution. There are methods based on surrogate explainability, in which the idea is to somehow approximate these complex models in some sort of locality using interpretable models. What do we mean by interpretable models? Models such as decision tree or linear model, they're very easy to digest, right? If you have a linear model, for instance, there's the coefficients of these features that somehow gives you an idea which feature is more important than others, right? So the idea in LIME is to somehow approximate this complex nonlinear model in some sort of locality of a particular individual or data point that you want to explain using a surrogate model, in this case, a linear function, right? And then they use those coefficients to rank the features based on their importance. Another popular methods for generating explanations are called counterfactual explanations, in which the idea is to somehow perturb input. For instance, perturb the input of Maeve so that the perturbed input, the updated input, so that the outcome of algorithm for the perturbed input changes, right? Perform some sort of minimal perturbation so that they can change the result of algorithm. The details are not important. Again, what's important is the following insight that I want to give you. It has been shown that these methods can lead to inconsistent, wrong, and unintuitive explanation, whether it is SHOP or LIME or these counterfactual explanations. All of them are wrong in general because they focus again on correlation between the input and output of an algorithm, as opposed to the causal relationship. And explanation similar to whatever we have discussed so far in this talk is a causal concept. We don't care about whether a feature, for instance, gender is associated or has a strong statistical association with an output of algorithm. We want to understand whether there's a causal relationship between them going on or not. And I think it's fair to say that the machine learning community, there is no agreement on what constitute an adequate and effective explanation in general. Researchers, they basically work with their own intuition of what explanation is. So it's a very messy area in general. So this made us to revisit the vast body of research in philosophy, cognitive science, psychology, on how human define, generate, select, evaluate, and present explanation. And we found two important things. Let me go through them. First, we understood that it is a common belief in psychology and cognitive science that people do not explain events as such, but explain causes of an event relative to some other event that did not occur. In other words, explanation should be contrastive. Why this and not that? This is how we explain whatever we observe this is how humans explain different sort of phenomena. Why this and not that? In the context of our running example, why the loan got rejected but not accepted? Secondly, I hope you are convinced by now that explanations are assignments of causal responsibility. We do not care about correlation. Our mind is a giant causal inference engine. We tend to interpret everything as if they are causal. We don't care about correlation. Correlations are useless for decision making. I mean, for certain sort of decision making, when we do predictive analysis, they might be fine, but for important decisions such as fairness of algorithm or generating algorithmic resource or generating result of machine learning algorithm, we definitely need to generate causal explanations. Based on these two somehow unique observations, we developed LEWIS. The paper just got into SIGMOD 2022. It's a joint work with my postdoc and a PhD student. With LEWIS, that's the unique feature of LEWIS. It brings the best of two worlds. It generates explanations that are both contrastive and causal at the same time. And there is no other methods out there that generate causal and contrastive explanations at the same time. Specifically, we propose novel explanations in SCORE that are based on probabilistic contrastive counterfactuals that are essentially a statement of the following form. What is the probability of an alternative output? This is the contrastive part. What is the probability of an alternative output had the value of an attribute been something other than the current value? This is the counterfactual part. Don't worry, I'm going to give you an example. And this is a very interesting observation. For users with negative outcome, such as Maeve in this case, as you observe, the outcome is positive, her application is rejected. These probabilistic contrastive counterfactuals, they equate to the common notion of sufficiency. We all know what sufficient causation means. And let me tell you why. Let's consider one feature, in this case, for instance, months. This month basically shows the duration of a bank account, right? Probabilistic contrastive counterfactual explanation for months, it evaluates the following statement. It quantifies the following statement. It quantifies to what extent hypothetically changing account duration or months from 24 to, let's say, 36 would lead to a different sort of outcome for me. To what extent hypothetically changing this factor would lead to a positive outcome, which essentially means to what extent changing this feature by means of intervention is sufficient for changing the outcome of algorithm. In other words, sufficiency addresses the tendency of an attribute to produce the desired outcome of an algorithm. So for those who receive outcome, we generate explanation in terms of to what extent changing each of their features can lead to positive outcome. It's both contrastive and counterfactual at the same time, and causal at the same time, or counterfactual at the same time. Similarly, for those who receive positive outcome, for instance, in this case, Irfan applications got approved, we somehow compute the dual notion. Contrastive counterfactual here, when you compute them for a feature against, let's suppose we want to generate explanation for months, we measure to what extent hypothetically changing 36, the current value, to 24 would change the results from positive to negative. In other words, we measure to what extent this feature is necessary for the positive outcome. These are basically fundamental notions. They're centered at the heart of how humans explain things, those necessity and sufficiency notion. We formalize these notions, and based on these two scores, our system generates basically wide ranges of local, global, and contextual and rule-based explanations, among which is the following one, which is interesting and important, which I'm going to explain quickly. Using the notion of sufficiency, or sufficiency score is sufficient counterfactuals, we generate what is called algorithmic recourse, which essentially provides the user with a set of actions, sort of recommendation. It's a set of action that if the user perform, they would be able to change the result of algorithm from negative to positive in future. It's just such a fundamental and important sort of explanation that we need to generate for users. In this case, the input, in order to generate this sort of counterfactual, these sort of recourses, the input to our system is a set of actionable variables that we accept as input. This is something that should be pre-specified by users. For instance, in this case, may tell us that saving and credit amount, they're actionables. Maeve can change them in future, but months, age, and name, of course, they're not actionable, right? They're immutable variables. Given these actionable variables, we capture counterfactual recourse as an optimization problem that seeks for a minimal perturbation. It's not a perturbation, minimal intervention, right? Minimal intervention that we can perform on these actionable variables such that we can change the result of algorithm with high probability. We are looking for an intervention which is sufficient for changing the outcome. We solve this optimization problem using integer programming. For example, the recourse generated by our system for this particular example shows something which is very intuitive and interesting. It says in order to change the result of algorithm, Maeve should change the credit amount from the current value to this one, and similarly changing the saving from the current value to this one. And if so, with high probability, maybe the application will get approved. Of course, under some assumptions. Okay, so the last thing that I want to discuss is, I'm not going to go through the details, but the scores that we propose in this work, they're basically counterfactuals. Computing and measuring these counterfactuals are even more difficult than interventions that we discuss in the context of algorithmic fairness and HIPDB. This is basically Pearl's ladder of causation. They are basically the most sort of complex queries that you can answer with data. Machine learning sits at the bottom of this ladder, association. This is prediction. Then we have interventions, which can be captured using the do operator. And then we have counterfactuals. Estimating or computing these counterfactuals from data requires very, very strong assumption. It basically, in order to compute them, you need to know everything. You need to know all the details and all the aspects of your underlying data generative process, which is very, very actually, which is a very strong assumption in real world. We don't know even the causal model, let alone the underlying structural equations, all these functional relationships. So in order to get rid of this, we had to actually establish theoretical results, which shows that under limited assumption about the underlying causal model, under limited assumption, can we somehow bound these scores? And then we basically theoretically establish results, which shows that under some assumptions, we can both bound these scores and we can actually compute them from data. I'm not going to go through the details. If you're interested, please check out the paper. We also have a very cool demo developed by a master's student at HDSI, which just got into VLDB. If you're interested, please go to the website of this project and check it out. It's a very cool demo. And with this, let me conclude here. We discuss, we're facing important challenges of algorithmic fairness, accuracy and reliability of the result we get out of the machine learning systems or data science pipeline, and algorithmic transparency and explainability. We discuss causal inference is important and an integral part of responsible data science, fundamentally required for reasoning about fairness and discrimination. It is important to use them for avoiding biased conclusion. It's a fundamental way to define and reason about bias, and it is crucial for generating explanations. And then we also discuss data management can be used for enforcing fairness constraints using sort of database repair or data cleaning algorithm. And it is also techniques from data management can be used for efficient discovery and recovery from different forms of bias. With this, I'm going to stop here. Thank you for listening. And I'll be happy to take questions about some of the things that I've discussed today. Thank you.
Cool. Thank you, Professor Salimi. So going back to HIPDB, there was a question in the chat. Parag, are you able to unmute? Or if you want, I can read the question.
Yeah, do you hear me?
Yes.
Yeah. So, Professor, the question was the query that you showed, that the rewriting of that query, did it happen under the hood as a part of HIPDB, or was it something that user had to actually write to get the desired results and the desired explanation?
Very good question. No, this is actually happens under the hood. It's a sort of, we are accounting for, so what HIPDB does is the following. It's a sort of causal inference. It first infer and discover all the potential confounding variables, right? By means of performing a bunch of conditional independence tests. And then given these confounding variables, it somehow rewrites the query to account for the influence. What this query does is something simple. It just takes weighted average. It first partitions data based on confounding factors. For instance, in this case, it partitioned data based on airport. It compares the delay in each of the airport, in each partition, and it takes weighted average. This is what it does. So it is being done totally automatically under the hood.
Yeah, that's what I expected. That's the real value added. Thanks.
Yeah.
Actually, can I follow up on that question? So I was curious if you have a latent that's not actually represented in your database. So let's say time of day is correlated with delays. And so Dallas, afternoon, many more delays than morning. And American flies more in the afternoon, United flies more in the morning, but I don't have time of flight in my database. Then I'm kind of up the creek, right?
Absolutely. So this is a fundamental problem in causal inference. What happens if you have latent factor? So there are basically two solutions for such cases. The first one is use what statisticians call sensitivity analysis, which essentially answers the following question. Is there any sort of, it evaluates the possibility of a latent factor, right, that can drastically change the results. It's sort of, in a sense, it gives you a bound. It gives you a bound that tells you, under now the assumption that there are some existing confounding factor, can we establish sort of bound on the credibility of these causal influences? This is the topic of sensitivity analysis. Another way to deal with this is to do latent variable modeling, right? If you know that there are latent variable, and if you know the causal structure, you would be able to do latent variable modeling. So there are classic way to do latent variable modeling, and there are novel way to do latent variable modeling. The novel way for doing latent variable modeling is using generative model, for instance. Variational autoencoders, what they do, they're latent variable model, right? They essentially infer the latent factor that essentially influenced what the encoders actually derive this latent representation. So then they have been applied in the context of causal inference as well, right? To infer, but they work on their assumptions, right? There's no magic if you're a latent factor. There's no magic that can save us. You can either bound. Again, those bounds also work on their assumptions. You need to make assumptions, distributional assumptions, for instance, over the confounding factors, the latent confounding factors. You know they're out there, but you also know, for instance, they follow a normal distribution, right? They're normally distributed, or they're discrete. I think the sensitivity analysis, most of the approaches they require to have discrete attributes, discrete latent factors.
All right, thanks for fleshing that out. All right, anybody else? Questions?
Yeah, I had a question. So how do you normalize, for example, in the admission thing? So there might be a different ratio of females to males in the entire on the planet, right? So how do you normalize for that? Like, do you just divide by the prior on the prior distribution on the females and the males or something?
When we take the weighted average?
Yeah. Or, I mean, how do you normalize for that?
So here we don't want to normalize by the normalization with respect to the normalization in this case. If you want to normalize, the normalization is with respect to the probability of applying for a particular department, not probability of having gender. Do I make sense? Okay, so that wouldn't make sense to apply the normalize by the probability of being a male or a female. No, it doesn't. That wouldn't work. Why that? Why does? Because the confounding factor here is basically different ratio of applications in different departments. So you basically need to partition your data based on department, take the averages inside each department, and then take weighted average. And weighted average depends on the probability of each department. I mean, but even within the department, you could take you could average by the or divide by the probability of being a male or a female, even within the department. I mean, why does that help? That's my question. I'm asking. No, it doesn't make sense to do that. I know what you say. So we need to normalize by inverse of the probability of receiving the treatment, which is in this case receiving confounding factor. So we need to normalize by probability of department. That's what I'm trying to say. You may have a situation in which you have another treatment and gender is a confounder, and you need to normalize by gender. But in this particular example, you need to normalize by applicant's choice of department. Yeah, exactly. That's what I'm saying. Like, wow, how do you determine that it's the department that matters, not the? Yeah. Oh, I see. The very good question. Very good question, but gets us to this point. Parallel causal inference engine. Here you go. So remember that I told you this engine gives you a recipe for estimation. Once you provide this engine with this basically causal model, it applies, for instance, there are sufficient and necessary condition that basically gives you a set of factors that you need to normalize with respect to those factors. Do I make sense? For instance, let me be more specific. There is a graphical criterion which is called backdoor criteria that you can apply to this graph and read all the necessary confounding factor that you need to do normalization. And it doesn't call normalization, it calls covariance adjustment. But if you may call it, if you wish to call it normalization, it gives you basically all the necessary, give you a sufficient set of confounding, right? That if you do normalization with respect to them, you would be able to have an unbiased estimate of causal effect. Did I answer your question?
Yeah, so I guess what you're saying is that that also needs to be determined.
Yes,
Yeah,
absolutely.
okay.
This is basically what causal inference is all about. Causal inference is all about coming up with the right statistical formula that you need to update, that you need to estimate. From how we can basically start from this background knowledge, right? To come with to get into a statistical formula that we can estimate. And this part is basically causal inference. From here on, it's basically a statistical inference.
Yep.
Causal inference is all about modeling. Capture your background knowledge in terms of this causal graph, and the graph tells you what factors that you need to adjust for or normalize with respect to those factors.
Very basic questions on the same top point. So the end result of all this was that the rows of data where gender was present, those got missing values, and it was still sufficient to create a good enough model, right? Is that what we achieved at the end when you data cleaning?
Oh, wait a second. They're actually two different issues. You're dealing with totally two different issues. One issue is how do you define fairness and how you can detect it. What we argued is fairness should be defined using causal inference. And if you want to detect it, you need to do causal inference, right? That's the detection issue, right? And for detecting it, you need to essentially have some sort of assumptions and data to impute these missing factors. You are right on that. Right? But now put that issue aside. Now we get to the second problem, which is different. The second problem is we are in the context of supervised learning. We have a training algorithm which we believe it's biased. It didn't pass the test in the first step. There are discrimination signals in it. And now we want to change data. We want to mess with this data such that we remove all the discrimination signals. And that part is a data cleaning problem. It has nothing to do with the causal inference. Right? But the constraint comes from causal inference. What is the constraint that we want to satisfy? That comes from the definition and causal inference. It comes from the model. The model tells you what constraint you need to satisfy. In this case, for instance, I did the modeling thing, right? Here, I decided that the data and the admission committee is totally discriminatory. Now we need to do something. What we need to do, we need to somehow change the data so that the updated data can be seen as a data which is collected from a word which we wish we had. What does that word look like? The word look like this. And this translates into a conditional independence. It's a constraint. It's a constraint. And other people, other researchers in the context of machine learning, the context of fair machine learning, they also implement fairness notion in terms of a constraint. Now, in order to satisfy this constraint, you can do three things. You can pre-process data. You can change data similar to what I did here. You can enforce this constraint, you integrate this constraint into the machine learning algorithm itself, which means solve a constraint optimization algorithm. Machine learning algorithm is an optimization problem, right? Add these fairness constraints as a regularizer. We could have done this here too, but since we are database people, we just want to mess with data. And you can post-process results. What I'm trying to say is decouple these two things together. One issue is how we can detect discrimination signal from data. One issue is now that we decided that the data is discriminatory, how we can change it so that we can remove the discrimination signal. So I hope I was clear enough.
Yeah, thanks.
Absolutely.
else, I think we'll make time for one more if there's a last question.
There are lots of interesting questions and things in the chat, but there are too many of them.
Can you hear me?
Yes.
Hi. So will this, with the result, I mean, with the solution you proposed here, like, implementing the D prime, will it also work if we have more and more admissible variables? Like what if you have more than department and qualification in this case? Will the performance of the low rank matrix factorization comes down, or did you get what my question is?
Yeah, that's a very good question. That's a very good question. If we have more and more admissible variables, it's like conditioning on a high dimensional set, right?
Yeah, exactly.
Yeah, and if you have like super large sets, then your data becomes sparse.
Yes.
Right, and then you are right on that the matrix factorization does not work, because you end up with like very sparse contingency tables or matrices for each basically value of these admissible variables, right?
Yeah.
Because what this conditional dependence means, it means for each state of P and Q or admissible variables, output and other variables should be independent, right?
Oh yeah, gotcha.
So partition your data, now you end up with like thousands of these small groups.
Yes.
So the contingency table or distribution, let's say call it distribution. The distribution inside each subset becomes very sparse. You have lots of zeros and few non-zero and integers, right?
Oh yeah, true.
And then the matrix factorization basically returns small numbers. It becomes very, very actually dense. And the bottom line is you get data which is crappy, very crappy. In that case, this method based on matrix maxstat works much better.
Oh, I see. Yeah.
But none of these are absolutely. But none of these approaches are perfect. I'm right now working on solving this problem in terms of what is called transport theory, which is a principal way to deal. I think, yeah, it's apparently you know what it is.
Yeah, I mean, I just asked you because the data set which we saw is pretty similar to the scenario where I work. I work in the Department of Medicine as a data scientist. So for that, the data we are currently, is having a kind of similar problems every time. I mean, like we are just handling with the manual solutions, but we haven't thought of this reason yet.
So I have an ongoing project which looks into it. I mean, if you're interested, and if you can share your data, that would be a perfect actually use case for my project. So please send me an email. I will be happy to discuss it.
I'll shoot you an email about it. No worries. Thank you so much for this.
Absolutely. Absolutely.
All right, cool. Well, we really appreciate your time tonight. The one thing I hate about Zoom is it's hard to do applause. So on behalf of everybody, I just want to say thank you for joining us tonight. We really appreciate you. Thanks for the talk. Absolutely, it was a pleasure. Thank you so much. Thanks for the interesting questions and interesting discussions, sorry. Yeah. All right. So I think we'll end the recording here, and we'll call it a night. Thanks everyone for joining us, and I hope to see many of you at future events. Yeah, absolutely. Goodbye. Thanks.
Thank you.